Welcome back. Today we're going to be talking about complex numbers and how to use them. So a complex number well, before we talk about complex number, we have to know what an imaginary number is. And that comes from, let's say, taking the square root of a negative number. So for instance, if r is a positive real number, then if we were to take the square root of negative r, then we can't do that because there's no number times itself that will give you a negative number. Because a positive times a positive is always a positive, and a negative times a negative is always a positive. So in this case, this creates what we call an imaginary number. So we deal with that by expressing this as I, which is this cursive I looking thing, and then the square root of r. So that is equal to the square root of a negative number. So for instance, if I have the square root of negative 3, that will be represented now as the I square root 3. Now, because of property 1, we could say that if we're to square I square root r, then that's going to equal negative r. So in other words, let's say r is 3. If we have I square root 3, well, this is like saying I square root 3 times I square root 3. So that's going to be I square root 3 times I square root 3. And I times I is going to give us I squared, and then square root of 3 times square root of 3 is 3. Well, I, which is actually can be written as, and you're going to want to write this down. I is equal to the square root of negative 1. So I times I is like saying the square root of negative 1 times the square root of negative 1. Okay, and that's going to give us negative 1. So therefore, negative 1 times 3 will give us negative 3. And that's why we have negative 3 here. Okay, so now let's talk about simplifying powers of I and the methodology we can use for that. So we know that I is equal to the square root of negative 1. And therefore, I squared is the square root of negative 1 times the square root of negative 1. Well, the square root of negative 1 times the square root of negative 1 is simply negative 1. So therefore, I squared is equal to negative 1. I cubed, well, that could be rewritten as I squared times I. Well, if I squared is negative 1, negative 1 times I is going to give us negative I. So I cubed is equal to negative I. And then I to the fourth, well, that's like saying I squared times I squared. And if I squared is negative 1, that's like saying negative 1 times negative 1, which is positive 1. So therefore, I to the fourth is equal to positive 1. Now, there is a methodology we can use here to find other powers of I and how we can simplify that. And it's based off of how many times I squared goes into an I value. So let's say that I have just I squared. I'm going to look at the exponent and I'm going to ask myself, how many times does 2 go into the exponent? So in this case, how many times does 2 go into 2? Well, it goes in there 1 time, and which is an odd number of times. So whenever something goes into there an odd number of times, that's going to mean that our sign is going to be negative. Okay? And if I were to look at I to the 4th, and I was asking myself, well, how many times does 2 go into there? That's going to go into it 2 times. So if it goes in there an even number of times, then it's going to be positive. So if I were to, let's say, do I to the cubed, then I'd say, well, how many times does 2 go into 3? Well, it goes in there 1 time, and then which tells me it's going to be a negative number, okay? And so it would be like a -1, and then we have times 1 extra I. So therefore it's going to be -I. Likewise, if it is if it's going to be an I, it's going to be a positive, which will be easier to illustrate if we do some other examples. So let's say I have I to the 6th. I to the 6th, I ask myself, well, how many times does 2 go into 6? It goes in there 3 times. So that 3 times, it goes in there evenly. So it's going to be a negative, and since it goes in there evenly, it's just going to be a -1. So I to the 6th is equal to -1. All right. Well, what about I to the 9th? Well, 2 doesn't go into 9 evenly. But it does go into 8 evenly. It goes in there 4 times, which is an even number of times. So that's going to tell me it's going to be positive. And then we're going to have 1 extra I. So that's going to be 1 times I. So that's going to be 1 times I. So my answer is just going to be I. And so I to the 9th is equal to I. I to the 22nd, well, it goes into 22 11 times evenly. So it's going to be either a 1 or a -1. Since it's an odd number of times, it's going to be negative. So I to 22 is equal to -1. I to the 83rd, same process. 2 doesn't go into 83 evenly, but 2 does go into 82 41 times, which is an odd number of times, which tells me it's negative, and therefore, and then we have, which is a -1, and therefore we have an extra I, the 83rd I, which then gives me -I. So that's the methodology we can use for simplifying powers of I. Okay, so let's talk about solving, quadratics and how imaginaries come into play. So here we have an example, like 2x squared plus 18 equals -72. So we only have a single x squared, so the best way of probably solving this is to take a square root. So we will start that process. We'll subtract 18 from both sides. So that's going to leave me with 2x squared equals -90. Then we'll divide by 2 on both sides. And so therefore x squared is equal to -45. Alright, so now we're going to take the square root of both sides. So I'm going to take the square root here, and I'm going to take a square root here. So remember, this is going to be plus or minus. Okay. Now I don't have to worry about it. I don't have to worry about it here. So that's just going to leave me with x equals plus or minus the square root of negative 45. Well, you can't take the square root of a negative number. That's a problem. So how do we do it? Well, we're going to evaluate the negative, and we're going to say, oh, well, x is equal to plus or minus I square root of 45. Okay, now we're on to something. But we're not done, because we want to present our answers in the simplest form, which means we want to, ask ourselves, are there any perfect squares that we can pull out of 45? Well, 45 is 9 times 5, so we can pull out a 9, and the square root of 9 is 3. So we write plus or minus 3i, and then we're left with just a square root of 5. So we have two imaginary answers. X equals plus 3i square root 5 and negative 3i square root 5. Okay, so now let's talk about complex numbers. Complex numbers have two parts to them. They have a real part and an imaginary part. And complex numbers represent all the numbers in the universe. They represent both all the real numbers as well as all the imaginary numbers. So this is our world of numbers. And so if I have a real number, real numbers, we could argue they have an imaginary component. Not really, but that imaginary component is where our value of b, our coefficient in front of I, is 0. So for instance, if I take, let's say, 3, which is my real part, a, plus 0i, well, 0 times I is just 0. So that's just going to be the number 3. And because we don't see the imaginary component to that. So complex numbers, which are also referred to as just imaginary numbers, have both a real part and imaginary part. So like in this case we have 2, which is our value of a, that's our real part, plus our imaginary part, 3i. And that's going to fall into the realm of all our imaginary numbers. But we have a subset of that called pure imaginary numbers. So opposite of, let's say, where the real numbers were, our b value is 0, we don't see an imaginary part. Pure imaginary numbers don't have a real part, so our a part is 0. So for instance, if I had 0 plus 2i, well, there is no real part to it, so we just write it as 2i. And this is a purely imaginary number because it doesn't have any real component to it. So let's look at how we can deal with these complex numbers. We're going to start off with some basic operations with them. So if we're going to add or subtract these numbers, we're going to add only the real parts to the real parts and the imaginary parts to the imaginary parts, because the real and the imaginary parts are incompatible. So here in this example, I'd add the sums a with c, which gives me a plus c, and then I would take the imaginary part bi and di, or the coefficients b and d and add those together. And the same can be said for subtraction. So you can't add the real with the imaginary. If you do, the universe explodes. So let's look at another. Well, let's just practice actually. So we're going to write an expression as a complex number in standard form, and I'm going to go ahead and combine the real parts together and then the imaginary parts. So here I'm adding these together. So that's going to leave me with 4, and then I'm going to add the 3 with the 11, and that's going to give me negative 8i. So that would be my simplified expression for that guy. Here I'm subtracting them, so keep in mind the subtraction sign applies to everything in the second one. So this is like saying I'm negative 24 and positive 9i. Make the sign changes to help you keep that straight. And that's going to leave me with 9, negative 9. So that's our real part. And our imaginary part, well, the negative 9i and the positive 9i cancel each other out. So we're left with just a real number. Actually, an integer, to be more specific. So negative 9. All right, see here, this is not just a, looks like, well, it's just a complex number and added or subtracted to another complex number, but we got, a real number, a complex number, and a purely imaginary number, and we're going to simplify this. So really I can just drop the parentheses. I don't need them. They don't really serve any purpose except for the minus sign here, which we apply for the negative 13, and then the 4i becomes negative as well. So when I simplify this, I'll be left with positive 22, because I've combined the 35 and the negative 13. And then the negative 4i plus I leaves me with negative 3i. So that's my simplified expression for that one. Okay, so now we're going to start multiplying complex numbers. So let's start off with this purely imaginary with the complex. And, well, they're both complex. I'm not using that correctly. But let's go ahead and we're just going to distribute this 5i to both terms. So it's going to be negative 40i minus, okay, so negative 5 times negative 9 gives me a positive 45, and then I times I gives me I squared. So we can simplify this further because I squared is equal to negative 1. And negative 1 times 45 is negative 45. And we're going to put that becomes the real part, okay, and we'll put that in front, and then behind that we'll put the imaginary part, minus 40i. So that is now simplified. For part B, I'm going to go ahead and combine my like terms here. I'm going to simplify this. So this is going to leave me with negative 6i times 4 minus 7i. And now we'll distribute the 6i to both terms. So that'll leave me with negative 24i plus 42 I squared. So that again, the I squared becomes a negative 1 and multiplied with 42 makes it negative 42 minus 24i. And we put the real part in front and the imaginary part. Now let's talk about simplifying quotients. So we want to simplify this part. We have a complex number in the top and a complex number in the bottom. To do this, we want to rationalize our denominator. We do not want an imaginary number in the denominator. So we're going to handle this the same way we would with radicals, and we're going to multiply both the numerator and denominator with the conjugate. So the conjugate of 5 minus I is going to be 5 plus I, and this is going to be 5 plus I on top. So the bottom part works just like a difference of squares. You got 5 times 5, which is 25, 5 times I, which is 5I, negative I times 5, which is negative 5I, and then negative I times I, which is negative I squared. So the shorthand on the denominator, I'm simply going to write this as 25, so it's just a difference of squares, minus I squared. Now, in the numerator, we're going to distribute the 3 to both parts. Here, so we're going to say 3 times 5, which is 15, 3 times I, which is plus 3I. Now we'll deal with the 4I, so 4I times 5 is 20I, and then 4I times I, which is going to give us a 4I squared. So now we will simplify the numerator and denominator. The numerator, we're just going to, I'm going to start off and combine our imaginary parts. So I'll have 15, and then 3 plus 20i, or 3i plus 20i is 23i. And then I squared is negative, so that's going to be negative 4, so minus 4. Down here in the denominator, I have 25 minus I squared. So that's like saying 25 minus negative 1, because I squared is negative 1. So really that's going to be saying plus 1. So to continue this, on the numerator, we have the 15 and negative 4, so that's going to become 11 for our real part, and then just plus 23i over, and then our denominator is 25 plus 1, which is 26, and that's going to be our simplified expression that has been rationalized, and there's no longer an imaginary number in the denominator. The last thing I want to talk about is how to graph on the complex plane. On the complex plane, it's broken into 2 parts, which is the real, which is our horizontal axis, and our vertical axis is the imaginary axis. So if we take a complex number, the real part of the number will be plotted here horizontally, where the imaginary part will be plotted vertically. For instance, if we were to take this first one, 3 negative 2, or 3 minus 2i, we would look at this and we'd see that, our horizontal axis is just numbered off 1, 2, 3, 4, just like we would with the Cartesian plane. But our imaginary one is going to be slightly different. We have 1i, 2i, and 3i. So for 3 minus 2i, I would go right 3, and that's going to take care of the real part, and then we go down 2. So that would be our point there. If I had, let's look at b here, minus 2 plus 4a, plus 4i, we would go start here at the origin, and we would go negative 2 on the real, and then up 4i on the imaginary. So that would be that one. So 3i has no real component, it's just purely imaginary, so therefore it's just on the imaginary axis. There's nothing real about it. And finally, D, we would go left 4 on the real and down 3i, and that would be that point. So anyway, that's complex numbers and how to work with them, and we'll be using them off and on. See you on the flip side.